All right, everybody, welcome to the second talk of today's Dots. We're very happy to have Professor Victor Zavala here, who is also known at Mad Victor Z on Twitter. You'll see him running in wild temperatures, recommending all sorts of beverages, posting on certain movies, and also serving as a very important mentor for the community. So we're very happy to have him here. So he is the Baldovan Dapra Professor in the Department of Chemical and Biological Engineering at University of Wisconsin-Madison, and a computational mathematician in the Mathematics and Computer Science Division at Argonne. He holds a bachelor's degree from the Universidad Iberoamericana and a PhD degree from CMU, both in chemical engineering. He is on the editorial board of the Journal of Process Control, Math Programming Computation, and Computers and Chemical Engineering. He is a recipient of the NSF and DOE Early Career Awards and of the Presidential Early Career Award for Scientists and Engineers. His research interests include computational modeling, statistics, control and optimization, and he uses integer programming techniques and some of these things, which I'm very happy that he'll be speaking about today.
Sounds great. Thank you so much, Alex, for the kind introduction. Let me tell you a little bit about the work that we're doing on optimizing supply chains. We came up with this very simple but potentially interesting idea for approximating the solution of these problems. These are large mixed interlinear programs. Just full disclosure, I am not an expert in combinatorial optimization, but you will see that some of the elements of complexity actually come more from the linear programming relaxation itself. So I think that might actually be helpful for the community. So in order to start, I really want to give a motivation. I come more from an applied side of things, so I'm a chemical engineer. So we're looking at applications, particularly in waste management, things that appear from food waste, organic waste. Today, I'm going to tell you a little bit about the dairy waste, the dairy industry, which is an important source of pollution, but also there are applications in plastic waste management. So you're going to find a lot of similarities in these three types of applications. How do you deal with large amounts of waste? And I like to motivate the discussion on the dairy industry with this simple question. What would be your guess of the per capita consumption of ice cream in the United States? So maybe just put it in the chat box and let's see what will be your guess. What is the per capita consumption of ice cream? I'll just monitor, here the answers. I'm starting to see 7 gallons per year, 7 gallons, right? So yeah, so most of you will guess like it's 7 gallons. So the answer for the US is 5 gallons per year, but there's actually a country that consumes 7 gallons per year, and that is New Zealand. So that is number one. So United States comes second, and something is going on down under. So in Australia also they're number 3, all right? So what these numbers tells you is that we value these products quite a bit, right? So, I mean, I would have never thought about consuming 7 gallons a year of ice cream. So since I moved to Wisconsin, I'm very close to that number. But what is fascinating about the dairy industry is that it's a very evolved industry. So there's been big advances in genetics and animal welfare that allows you to produce a lot of milk through cows. Just to give you an idea, a single average cow will produce around 2,000 gallons per year of ice cream. That's just one cow. So that will be enough to provide ice cream for 180 Americans, right? So probably that's the origin of the expression holy cow, right? So these animals are pretty miraculous, right? They can do a lot for us. But like with any industrial process, every time you produce a valuable product, you also produce products that you don't want to deal with. So these are byproducts. And unfortunately, a cow is just like a human being, right? It's a chemical reactor, so it produces milk, but also produces manure. So, and the problem with cows is that they produce a lot of manure. So you are producing on average 20 tons of manure per year for a single cow. Just to put it in perspective and hope that this doesn't ruin ice cream for you forever, but that's around 4 gallons of manure per gallon of ice cream. So that tells you just how inefficient actually the industry can be from that perspective. So we produce a lot of waste as a result of this. And in certain places of the US, like Wisconsin, California, Texas, we have high concentration of animals. So just to give an idea, there are 1.2 million cows in Wisconsin alone. There are 9 million in the United States. So what is the big issue with manure? So manure is a very complicated waste stream. So it contains a lot of nutrients that come through the feed of the cows. So most of the cows will eat grass or they will eat corn. So that is concentrating phosphorus and nitrogen. I will explain to you in a second why that is a problem. And also they contain organic matter, and this degrades and leaks methane into the environment. So methane is a very powerful greenhouse gas emission. Greenhouse gas pollutant. So yeah, it's a complicated waste stream that can produce a lot of problems. But at the same time, you can think about this as a resource, right? So if you have the ability to recover these nutrients, so for example, what the farmers will do will be apply manure into the field to use those nutrients for growing crops. So that has been a practice for many centuries or millennia. Then that is great, right? At the same time, you could potentially recover this methane and use it as natural gas to power electricity or any sort of power generation equipment, right? So that could provide a lot of electricity for homes. But now the complication here with manure is that it's a wastewater stream. It's 93% water, so it's actually hard to move around. So this is the idea, right? So you say, well, we have this waste stream. It's a lot of it. So what can we do with it? So there are chemical processes, so biochemical processes that allow you to recover methane, that allow you to recover nutrients from this manure. So for example, there's this product called struvite, which is a crystal that you can use actually as a fertilizer, or you can use it even in salmon farms to grow fish. So that's a great source of nutrients. And you can produce electricity, you can use biogas to power vehicles or the power grid, for example. So there are many technologies and many products that you can envision. But the problem with any waste stream like this one is that the cows are not in one location, so they're highly distributed throughout the United States. So I'm going to show you a picture in a second. Just in Wisconsin here, I'm showing you a map of the different big dairy farms that we have. So what happens with these cows is that they're distributed, but at the same time, there's certain areas where they are highly concentrated, and this tends to concentrate the waste. And it's not easy for the farmers to deal with that waste. So when they apply it on land, they're going to tend to oversaturate the land with nutrients. So I'll show you how this looks like in the next slide. So transportation is a big obstacle. So once the manure is produced, a lot of water, farmers have a hard time dealing with it. And as a result of that, they tend to apply it on land nearby, and that creates a big pollution problem. So this is how the pollution looks like. So we have places in Wisconsin here, in this particular area, where we have a lot of phosphorus that has been accumulated over decades or centuries now, where these nutrients remain on the soil. It's much more than enough for the plants to absorb. So the plants are actually not benefiting anymore from this phosphorus. And what ends up happening is that this phosphorus is going to end up in the lakes. So every time we have rainfall, every time we have snow melting during winter, all this phosphorus will go to the lakes, and that starts creating and promoting the growth of algae, right? Now, this is not a problem only of Wisconsin. So we have high concentration of animals all over the state, different parts of the country. You see that there's a big concentration of animals here in the Midwest. We have big concentration of animals here in California, for example, even in places like Florida, so where Alex is. So yeah, this is a big problem, right? So it's not unique to Wisconsin. And as a result of that, you see that nutrient pollution indeed is a problem, not only Wisconsin, it's the entire Midwest region. We have problems here in California, we have problems here in Florida, right? And this is triggering a lot of problems in terms of nutrient pollution. Now, the reason why nutrient pollution is a problem is that these nutrients don't stay in the soil, so they tend to leak to water bodies. So here is just a picture of the Mississippi watershed. That if I create pollution in Wisconsin, it's not going to stay in Wisconsin. It's probably going to affect also our neighboring states. In fact, many of the nutrients that we end up applying in the Midwest here are going to end up and maybe made it all the way to Gulf of Mexico. So maybe you have heard in the news that this part of the Gulf of Mexico, the delta of the Mississippi, is heavily polluted with nutrients. Right now it's a dead zone, so it's creating a lot of environmental problems, right? So how does nutrient pollution looks like? So one of the big problems that we have been facing is the increasing severity and also frequency of algae blooms. So here is Lake Erie, close to Pennsylvania. This is the terrace close to Madison. So what you see is these events of algae blooms coming. And the reason for that is that we have saturated the water with nutrients, and algae, think about it as plants, right? So they absorb the nutrients. When the solar radiation and the temperature conditions are right, they're going to create a big, fast growth. and that creates start polluting the problem. And as I said, this is not a problem just of Wisconsin, but like the entire US basically has been seeing an increasing amount of algae blooms, including places like Florida, for example, or California. So how do you solve this problem, right? So the recognition here is that this is a supply chain modeling problem. You can think about it that way. So what you want to do is to design an infrastructure for installing technologies at strategic places that can take this manure, transform it, process it to recover these nutrients, to recover methane. And also this infrastructure will have to do the transportation, right? So you can do this by truck hauling, or you can do different types of techniques or technologies for doing the transformation. So this is the type of models that we've been developing in my group. At first hand, this looks like a very simple problem. I'm going to show you that the problem is the size of the problem and also the coupling that arises in these types of problems. But just to give you a very quick overview of what it is a supply chain problem. So we have a set of consumers for manure or products that can be derived. We have suppliers of these waste or potential products in the system. We have transportation and we have processing. We have typical balances. So think about this as nodal balances for all the products, right? So it's a simple balance of where the waste and where the products are coming into play. So this is not too complicated. The big complication comes from actually the transformation. So the problem here is that we have waste that can be used to produce many different types of products. So you have biogas, and then biogas can be produced into electricity. So that creates a lot of interdependencies in different types of products and creates a lot of complicated coupling. We also have typical like capacity constraints, right? Now, this problem that I'm showing you here is a linear programming problem. So this is assuming that the technologies already have been placed. So later I'm going to show you what happens when you develop a mixed integer problem where you actually have to make decisions about where do you place those technologies and how big they have to be. All right, but let's start just with a linear programming problem. Now, an important observation here, right, is that this linear program embeds a very complex graph topology. Typically, when we think in terms of supply chains, we think of the graph as a spatial graph, right? So we have interdependencies between different geographical regions, between suppliers, consumer technologies, and final destination of products. But another interesting observation is that you can visualize this graph more in the product space. This product space is very important for the chemical engineers or biochemical engineers, because what ends up happening here is that the products get transformed. So as I was saying, you can have, let's say, manure entering that technology. This manure gets used to produce, let's say, biogas. Then biogas is propagated to produce electricity, and then that electricity is provided to the power grid. So this creates some very interesting connections between products. This is different from the traditional network flow type of problems that we have seen in the OR community, where typically the products are not interdependent, right? You can have multiple products being exchanged, but there's no transformation between the products. So this creates very interesting coupling between geographic location and also product locations. And as you might expect, the problem also becomes complicated because you have dynamic effects. The problem with manure management or waste management is that it's strongly seasonal. So you don't generate the same, you are always generating manure, but the problems that you see tend to be seasonal. For example, the algae blooms will appear during summer. They don't appear during winter. And this is because you are influenced by weather temperature. So that for weather conditions like temperature or solar radiation. So that means that the supply chain is dynamic, right? And that means that you have also coupling across time. And the nice thing about having a graph structure behind the scenes is that you can actually use the graph representation to think about the coupling now between geographical, product, and also temporal locations in a unified way. So I think this is one nice thing of thinking about this problem as a graph. And this also facilitates modeling of transportation delays, inventories, and dynamic resources. So we're developing currently models that allow you to couple all these interdependencies in a unified manner. Now, what this tells you also is that now the complexity grows even more, right? So now you have to think about space, time, and also the many different products that you can have in the system. Now, how do we use these models, right? So these models, we develop them And then we use them to inform policymakers like the EPA. Where do they need to place technologies, and at what cost will they be seeing the generation of different products? And the EPA uses this type of information to say, well, you know what, we might need to create incentives for some of these technologies. We might need to intervene in certain areas. And we use this to just inform the public, like what can you do if waste management becomes a problem? Can you install new technologies? Do they exist current solutions, or what type of government incentives you want to deploy, right? Now, one of the things that we have identified as part of these studies is that in the United States, at least, the government doesn't like to install technologies for people, right? So typically they're going to think about incentives that will activate a market, right? And they want to see a market being created for exchanging these products, right? So you could say, I can transact manure to produce biogas, and then that biogas can be sold to the power grid, right? So you're activating a market. So one nice benefit of this modeling framework that we've been developing is that you can actually think about it as a market clearing problem. So this formulation actually has its origins in the power grid market clearing problems that I have actually been working on for the last 5-7 years now. So where the idea is that you think about this formulation in exactly the same way that we were thinking about it before. So it's just consumers, suppliers, transportation, and technology providers. But you think about the meaning of this problem in a different setting, as opposed to try to think about this as being as a central planner type of thing. You think about it more as a market clearing formulation where you have all these stakeholders providing bid prices, providing capacities for their technologies or their different offerings. And then this entity will generate allocations in the system, and at the same time will generate clearing prices. Now, this provides a framework to enable coordination between different stakeholders, which is very important in these types of problems. Now, this has a lot of economic properties that I don't have time to go over, but I'm happy to share the slides with you if you're interested about this. But this has very similar type of economic properties to the ones that you see in coordinated markets like the power grid, okay? So I'm gonna skip this in the interest of time. Now, the mixed integer formulation is a very simple formulation. I don't think that from a combinatorial standpoint has any particular challenge. It's really more the scale of the problem. So the idea now is that I augment my supply chain model by taking into consideration the potential installation of technologies. So this is something that is called a capacity expansion problem. And the integer variables, the binary variables, for example, will influence the capacity constraints of the system, right? The ability of these technologies to participate or not into the system or in the market. So the big complication of the problem is the scale. So we have many possible transportation paths for the different products. We have the conversion of these products, and that creates a very dense graph that you need to take into consideration, right? Now, another related question here is that we're not only interested in just solving the problem, but really one of the questions of the EPA or a lot of government initiatives is what resolution do you really need to solve this problem? Do you need to solve this problem at the state level or at a regional level or at a county level or at a national scale? So we also want to get a little bit of insight about that, because it's going to be nearly impossible to form a problem that solves the entire thing at once for the United States, right? But we potentially can provide some insight into what level of aggregation you might need into the system, right? So finally, this gets me into the core of the problem. So I motivated the problem a little bit, show you a little bit the model that we have. It's a big mixed interlinear program, big scale. A lot of the graph embedded in it is tightly coupled. It's very hard to decouple, to decompose actually. So that limits some of the things that you can do with decomposition, for example. So one of the things that we were thinking about is, well, precisely driven by that idea of how do we coarsen this graph, what level of aggregation or resolution we need, maybe we can come up with something simpler that we can use. So we came up with this very simple idea. We say, you know what, this graph is very dense, has many possible edges. So how about we try to do some sort of sampling scheme where I try to randomize the selection of certain edges. That will give you a very natural way to approximate the solution. So it will give you potentially a feasible solution with a very sparse graph. And then that will naturally give me a lower bound because it's a maximization problem, right? So this will be an easy way of constructing a feasible solution. We took a little bit of inspiration from graph sampling through these ideas of a scenario sampling that happen in stochastic programming, because typically the observation in sample average approximation and stochastic programming, for example, is that you can actually get some very tight estimates. You can get high quality solutions quickly with a small number of scenarios in that context, right? So the observation here is that maybe if we can sample enough edges, we can actually get a high quality solution, and potentially we can even estimate the variance of the solution. So I do think that random sampling gives an interesting paradigm for trying to understand some of the statistics of the solution and the quality of the bounds that you actually have. So we're bringing some of those ideas in this particular context, right? Now this will give you potentially a good feasible solution. But now the question is, how do I get an upper bound, right, in this case? So in this case, paradigm that you can use is actually aggregation or coarsening. So the way that we are doing this, and this is nothing new, so people have looking into this in different domains, is just really trying to coarsen the graph. Now, coarsening is something that is strongly application dependent, okay? But in the context of which we're using it here, it's actually quite straightforward to do it. So the idea here is that we're going to select randomly as a collection of nodes. And around each one of those nodes, we're going to aggregate the edges or the nodes inside this particular problem. This is going to let me into eliminating all the internal edges inside that a particular partition. But the problem that we encounter in our particular application is that this is going to leave still a lot of edges that communicate across the partitions, because we have a lot of products that can be exchanged between these two partitions. So another thing that we do in this particular coarsening procedure is that we aggregate those edges as well. And that tends to eliminate a lot of edges and potentially you obtain a very coarse graph, right? So this is how the procedure looks like, just with a quite big, just a simple illustration. So we select a set of pivot nodes. Then we create partitions based on those pivot nodes, based on the nearest neighbors, and then we aggregate. That eliminates the local edges, and then we tend to eliminate also the edges, right? And as we might expect, as we increase the number of pivot nodes, then you might expect a higher quality solution that you can potentially navigate. Now, I don't have too much time to go into the details of how do we do it, but you might expect that the aggregation process is actually not that complicated. So the idea is that we aggregate the feasible set, right? So we take the node balances, split them into different domains that is facilitated by the graph abstraction through the coarsening, right? So we're just going to do node aggregation that is going to eliminate the edges, and that leaves me with a smaller set of nodal balances with a linear combination, very simple. Then we also do edge aggregation, as I was mentioning before. So this can be done very simply by just aggregating the flow constraints in the system and by defining aggregated global flows. And that gives me a small subset of edges that we have in the system. So at the end of you also aggregate the objective function, but that's quite straightforward to do. But it's just neglecting the cost of some of the local edges, and it gives you a natural upper bound for the system. But just if I could just summarize, what we do is we just take an aggregated view of the system. We aggregate the nodes in a particular partition. We aggregate the edges that are coming across the partition. And this aggregation procedure, you can show that it provides a valid upper bound, okay? And as I said, this is facilitated by the graph abstraction. It's nothing too sophisticated, but it's application dependent. And there are many ways that you can do it. We have found a good way to do it in this particular context. Now, the good thing about this is that this gives me an opportunity to estimate an optimality gap. The reason why I think this is relevant is that there have been tons of studies in the context of the application that I was telling you about in waste management and biomass processing, where people construct approximations of the problem at different levels of aggregation. They say, I'm going to aggregate this particular region, I'm going to aggregate this particular county or this particular state, but they do not have a mechanism to understand what is the quality of that approximation, right? So through this mechanism that we have here, at least we have a way of knowing in what region the solution should be, right? At least we know the gap, right? All right, so let me conclude with a simple case study just to give you an idea of how this thing scales. So this is a case study where we're precisely trying to take the manure from the dairy farms, right? We're going to put it in technologies. So we're going to decide how many technologies and where we're going to place them. We're going to process this to obtain a fertilizer. And this fertilizer, we can sell it to croplands, or we can sell it to external companies that can be commercializing this fertilizer. This fertilizer can come in the form of these pellets that actually you can sell, and also of struvite, which is this crystal that you can actually commercialize as well. So this is the study region. So this is the University of Wisconsin-Madison, is located right here. This is a big lake that we have nearby, and you can see the location of all the farms here. So this is real data, okay? So you can see that we are surrounded by a lot of dairy farms, and we're surrounded by a lot of farms that are using that manure to fertilize the land, right? And surprisingly, or not surprisingly enough, we have a lot of algae blooms in this particular lake, right? So we're precisely trying to build a supply chain that will help us understand how do we deal with this problem. So the reason why I bring this up is that just this study region, we're talking about this very small area in Wisconsin, right? It's a very, very small area in Wisconsin that already contains 1,300 nodes. It's an MILP that contains, or it's a graph that will contain 1.8 million edges. So those captures all the possibilities of transporting manure between all these different croplands. There are 12 different technology types that we can install, and we have 20 different products that you can recover, right? So this problem already gives you an MILP with 32 million variables. Around 10,000 of those are binary variables. So as I said, the binary variables are really not the problem, it's really the size of the problem itself. So yeah, this is a big problem, right? So precisely what we did was to do our aggregation procedure, all right, and our sampling procedure. So you see here from sampling, right, that you start increasing the number of edges and quickly the optimality gaps start shrinking. So that has been an interesting observation. You see also that we get a very tight upper bound right away, which has been also quite a surprise. So we need actually few partitions to do this. And the kind of surprising result that we have is that we only require 100,000 edges in the graph, which is 5% of the total number of edges that you have in the graph, to already achieve a 4.57 optimality gap. So this starts also giving you insights of the level of resolution that you actually need in the system. So this is good insight just for the EPA itself, because it's starting telling them, you know what, it's not necessary to go at this super high level of resolution inside every one of the farms in the region. You can probably aggregate quite a bit, right? So this reduces the size of the problem quite significantly and shrinks the gap very, very quickly. So we've been doing comparisons as well with Gurobi. As you can see from this graph, it's quite obvious, right? The problem with Gurobi is not the efficiency of Gurobi itself, it's just that you're stuck in the root node trying to solve the LP, right? The LP relaxation. So once you solve this LP relaxation, you can make very quick improvement. So again, this just tells you that it's really not the combinatorial aspect, the one that is really affecting us, it's really just the magnitude of the LP relaxation. So one of the good things with this approach is that we can actually get high quality solutions just with a smaller budget of time and also aggregation. So I think that this is good. So in the future, we're going to start comparing with other approaches like column generation and other aggregation approaches that we're currently considering. So with that, I will conclude the presentation. If there's time for questions right now, we can take them, and I will also be available through the breakout rooms in case you want to ask more questions. And also we have coding, Julia, in case that you want to solve these problems or try to think about how do you model supply chains. So thank you for your attention.
Thank you so much. I think we can take time for maybe just one question here, and then we can move on to the breakout rooms.
Yep.
I'll give it just 35 to 10 seconds if somebody wants to raise their hand or write in the chat. If you want to raise your hand, then I can call on you. Ah, yes, we have one. And I think you had answered this possibly before, but Yuan asks, how is the graph sampling done? Is it random, or is it selective, adaptive by a certain criteria?
Yes. Yeah, that's a great question. So at this point, we decided to start with pure random sampling because we wanted to estimate the variance and try to come up with some estimates of that variance. We're trying to show that actually you can get some statistical estimate of this bound. So this is similar in essence to Monte Carlo sampling, if you want to think about it that way, that is using sample average approximation. But there's definitely more tailored approaches that you could use. One big factor that you can use to run this sampling is simply based on distance. So you know that there are going to be edges that are going to be highly unlikely to be part of the solution set. They're going to be in the solution because it's just going to be nearly impossible to transport manure or a certain product across a certain region. So you can envision different ways of doing that sampling procedure to try to mitigate variance more quickly. So yeah, at this point, we only tried random sampling just to do those estimates. Thank you for the question.
Well, thank you for the answer and thank you for the talk. So in the interest of time, I will take the next questions off to the breakout rooms. So let's thank both of our speakers today again.
Yep.
And thank you everyone for coming. And for those of you who have to leave, we'll see you next month.